we're going to consider some object falling through a fluid. So if I have an object falling through a fluid, gravitational force is pulling it down, drag force is pushing it up. I could possibly have a buoyant force depending on the relative densities of the solid object and the fluid. So that may be there, may not be there. If I had a situation like a hot air balloon, then the buoyant force is what actually causes it to rise. So I could also have a similar situation where the object is actually rising, like a hot air balloon, in which case the drag force acts downwards, not upwards the way I've drawn it. So what I'm doing right now is for a falling object, look at Newton's second law. Mass times acceleration is all my forces. So drag force going up, gravitational force, weight going down, ignoring buoyant force for now. Terminal velocity, acceleration 0. So that means that this whole equation 0. So Fd equals Fg. Drag force, we know from last lesson, 1/2 CD rho v squared area. Gravitational force, weight, mass times gravity. So my terminal velocity, solve this equation, 2mg over CD rho Fa. So again, this is for the simple case of no buoyant force, object falling. Any other scenario, do exactly the same way. All the forces, so whether they have buoyant force or not, drag force going up or down, make sure it has the right sign, and then just terminal velocity equals 0, set it up, drag force, buoyant force, weight, whatever you have, solve for your velocity, that's your terminal velocity. So again, for my hot air balloon, I would have buoyancy pushing it up, gravity pulling it down, drag force pulling it down. This is of course assuming that the hot air balloon is going up. Hot air balloon could also be going down, in which case force of drag goes the opposite direction. But again, all I need to do is set up my sum of forces. In this case, going up, I have buoyant force, and because it's going up, drag force going down, gravity always going down, equals mass times acceleration, but acceleration 0 at terminal velocity. So buoyant force, remember this, density of the fluid, volume times gravity, and then these guys, gravity, weight, and drag force 1/2 CD rho v squared A. Again, your area is whatever area I'm dealing with, cross-sectional area for the sphere or whatever other object I have. CD values, A values can be found in the previous lesson. Alright, so example of this, I want to find the terminal velocity of a hailstone, diameter 1/8 of an inch, assuming it's a perfect sphere. Also going to assume that ambient temperature is 14.5 psia, temperature is 30 degrees Fahrenheit, and the specific weight of this hailstone is 49 pounds per cubic foot. So what we have is my hailstone falling, so gravity pulling it down, drag force pulling it up. So just like the previous situation, we have these two forces, drag force going up, gravity going down, and they add to 0 at terminal velocity. I didn't assume any buoyant force because the weight of water or hailstone, 49 pounds per cubic foot, is a lot heavier than the air. So buoyant force is not very applicable here. If you add it in, it's fine. It's just extra work. It doesn't give you that much better results. So drag force, 1/2 CD rho of the fluid, v squared A, is weight of my hailstone. Now in terms of weight of my hailstone, the mass is density times volume, so density of the solid object times volume, and then density times gravity is specific weight. So know that number, 49, put it in there. Then solving this equation for my velocity, so I have 2 gamma b over CD, density of the air, and area. Then because I'm assuming this is a perfect sphere, volume of the sphere in terms of diameter is pi over 6 d cubed, area is pi over 4 d squared, so I can put that in for volume, that in for area, like I did down here, and then the pi's cancel, a couple of numbers cancel, some of the d's cancel. So overall equation for terminal velocity, 4 gamma d over 3 CD density of air. Now, I know gamma, I know d, I do not know CD, and I do not know the density of the fluid, so that's what we need to do next. So density of the air is the easier of the two unknowns. Simple ideal gas law, so pressure is density R times T, so my density is pressure over RT. Pressure 14.5 psi, it's already absolute, so that's good, but we also want it in PSF instead of PSI, so good old 144 square inches per square foot there. And then are 1,716 pounds-feet per slug degree ranking in English units. And then my temperature, 30 degrees Fahrenheit, want to get that into ranking, so add 460 to get that to absolute temperature. It gives you 0.00248 slugs per cubic feet for the density of air. So CD value, want to figure out what CD is. So what we have here is a perfect sphere. So we know from the drag lesson that we can find the CD value for a perfect sphere in figure 11.2. So here's figure 11.2. Saw that in the last lesson for spheres and cylinders. So for this case, want the blue line indicating a smooth sphere. So all we need to do is find the Reynolds number on the x-axis, go up to the blue line, then go over to the y-axis to find our CD values. You can see from that figure that the drag coefficient CD depends on the Reynolds number, and the Reynolds number depends on velocity, and velocity is what we're trying to find. So because we don't know velocity, we don't know Reynolds number, which means we can't find CD. So now what do we do? And the answer to that is to iterate. So in other words, guess a value for CD. So I'm going to guess that CD is roughly 0.5. That's a pretty good guess for most spheres anyway. So put 0.5 in there with the previous value of density that I found before. It's going to give me some value of V. Now, because I just guessed the value of CD, I don't know whether it's going to be right or not. But what I can do is that it's going to give me an initial guess for V. And then with that initial guess for V, I can find a Reynolds number. From that Reynolds number, I can find a CD value. If that CD value is the same as one I guessed, it's the right answer. If it's not, I can use that new CD value in there, get a new velocity, find a Reynolds number, find a new CD, and keep on going until I get the same CD value. So as I said, plug in my guess of CD 0.5 in this equation with my previous value of rho f that I had before, gamma 49, diameter 0.125. Also want that in feet, so divide by 12. Plugging all that in gives me an initial first guess of 23.4 feet per second. Now as I said, I don't know if that's right or not, so I want to check it. So first thing I want to do is find the Reynolds number. So Reynolds number, velocity, diameter over kinematic viscosity. Velocity 23.4 feet per second. Diameter, again 0.125. Turn that into feet, divide by 12. And then the kinematic viscosity of air at 30 degrees Fahrenheit, I can find that in table B8, 1.42 times 10 to the negative 4 feet squared per second. That gives me a Reynolds number of 1,717. Now what I want to do is look at that on figure 11.2 and see if that gives me a CD value of 0.5 or not. So that's the next thing we want to do. So here's my value of 1,717 for the Reynolds number on figure 11.2. Be careful with this logarithmic scale. Sometimes students have a hard time reading it. 10 to the 0 is 1, 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000. So basically going up by factors of 10, 1, 10, 100, 1,000, 10,000, 100,000, a million. Then every line in between there is kind of a division. So if you start at 10 to the 0, which is 1, the next line will be 2, next line will be 3, 4, 5, 6, 7, 8, 9. Then you get up to 10 to the 1, which is 10. So in our case, we have 1,717. So 10 to the third, that's 1,000. The next line over to the right of our green line would be 2,000. So our green line, somewhere between 1,000 and 2,000, a little more than 2/3 of the way. So there's 1717 from our Reynolds number. And as we said, we go up to the blue line and hit the blue line, go over to the y-axis. Y-axis is our CD numbers. Again, same deal here, logarithmic scale. So 10 to the negative 1 is 0.1, 10 to the 0 is 1. Each little division is then 0.2, 0.3, 0.4, 0.5. So I can see that the green line ends up between my divisions of 0.4 and 0.5, closer to 0.4, so somewhere around 0.42 would be our first guess for CD. So as just saw from the figure, CD value roughly 0.42 for this case, not the same as the 0.5 that we guessed. So we know our answer is not right. So we need to do this again. So with a new guess value of 0.42, plug that into this equation. So basically same numbers everywhere other than 0.42 was 0.5 before. So plug all those numbers in, get a slightly different velocity, 25.6 now. And of course, again, we don't know if that's right or not, so we need to check this just like we did before. So find the Reynolds number for this new velocity. So again, all the same numbers, just a new velocity gives me a new Reynolds number of 1,875. Now go back to the figure to see what the CD value is. So again, here's figure 11.2. Green line, Reynolds number of 1,875, so a little bit closer to that 2,000 mark. So green line shifted a bit to the right, but not that much. Goes up, hits the blue line, back over, and pretty much the same number, 0.42 for the CD value. End up with the same answer. CD is still 0.42. That means that is the right answer. So because it's the right answer, the velocity we had before, 25.6 feet per second, is the correct value for the terminal velocity in this case.